Okay, we're going to do 2A, B, and C. So, a bike rider approaches a hill with a speed of 8.5 meters per second. The total mass of the bike and the rider is 85 kilograms. Okay, so as always, what I want to do is I want to put the information they give us off to the left. So the first thing they give us is velocity. An initial velocity at that equals 8.5 meters per second. And then mass equals 85 kilograms. Okay, so we got to find the kinetic energy. So this one should be an easy one because they give us everything we need. So the first thing we're going to do is we're going to write down the formula without everything in it. Kinetic energy equals 1/2 mass times velocity squared. Okay, so next thing we're going to do is we're going to plug everything in. So we're going to write kinetic energy equals 1/2. The mass is 85. Parentheses. The velocity is 8.5. And then squared. Right? So 1/2 times 85 times 8.5 squared. So punch that in the calculator and you should get kinetic energy equals 3070.63 joules, something like that. And it might, you might have it in scientific notation. You could say like 3.1 times 10 to the 3 joules. If you wanted to do that, and that would be fine. So there's our kinetic energy. This one's pretty straightforward, pretty easy. Let's move on to the next one. Next one gets a little bit trickier, I guess you'd say. The rider coasts up the hill, assuming there's no friction. At what height will the bike come to a stop? So when you got to think about this one, remember, let's just assume the hill is infinite, right? So that means he's not going to come to the stop at the top of the hill. We're just looking at what point on the hill it'll come to the stop. He'll come to a stop, right? So we're going to use our conservation of energy formula. So we have our initial kinetic energy plus our initial potential energy equals our final kinetic energy plus our final potential energy, right? So he's moving right along. So let's see, here we go. Okay, so a couple things to remember or think about for this one. It's a little bit different. We're used to zeroing out certain things, but let's look back at A. It says the bike rider approaches a hill with this speed and this velocity. So let's draw this real quick, just so you guys can see. He's going on a flat plane, right? So this is our bike rider. Bam, bam. Yeah, there we go. That's good enough. So he's approaching the hill, right? Which means what? He already has speed, because remember, it says he's going 8.5 meters per second. So that means he already has kinetic energy. So normally we're used to saying kinetic energy, initial kinetic energy is 0. Well, we proved that, it isn't 0. He has kinetic energy, right? But what he doesn't have is potential energy, because look, there's no more going down, right? Because remember, our formula for potential energy, let's write that off to the side, equals equals mass times gravity times height. Well, remember, in this case, his height is 0 because he's at the bottom of the hill, right? So what does that mean? That means that his potential energy is 0. Okay, his initial potential energy is 0 because his height is 0. His initial kinetic energy, well, we just said it. So let's just call that, let's round it and say 3070. Okay, so we have his initial kinetic energy and his potential energy is 0. And remember, what height will the bike come to a stop? When it stopped, what does that mean? That means that the kinetic energy will be 0, right? So we know that the final kinetic energy will be 0. Okay? So at this point, what's our formula for potential energy? Well, it is mass times gravity times height. Mass times gravity times height. So let's bring all this together. At this point we have 3,070, because that's our initial kinetic energy, equals mass is what? Where's our mass? 85 times gravity, that's 9.8, times height, we don't know, right? Because that's what we're trying to find. So we have an 85 times 9.8 times h equals 3,070. So let's bring it all in. So we have, let's bring this up here. So we have 3,070 equals about 833 h. Now we're back to basic algebra, right? Let's make this triangle a little bit better. There we go. Now that's a good triangle. Okay, so divide 833, our basic algebra, cancel that, do the same thing to this side, and now we have our height. When it comes to a stop is 3.7 meters. Should have got something like that. Depending on if you round this kinetic energy, you might have gotten a tiny bit off, but that's about what you should get. Okay, so final question. Does your answer depend on the mass of the bike and rider? Explain. So with this kind of question, I guess it could go either way, when you think about it, but let's look at this. Let's look at what was not zeroed out. So we ended up with kinetic energy initial equals potential energy final. So let's look at these formulas. 1/2 times mass times velocity squared equals mass times gravity times height. Okay, well, I'm seeing something that's consistent on both sides, right? There's mass on both sides. So does your answer depend on mass? So if we took out mass completely, would that change the answer? Well, let's look at this. If we divided mass out, because you can divide letters out, right? It means you divide it out on this side. Well, now our mass is completely out. We took it out completely because we canceled it out on both sides, right? So no, it doesn't. Mass is it's a factor for both sides, which means you can factor it out. So it's fine. So that's going to show up later in this unit where they might give you, they're asking you for, let's say, height, but they don't give you mass. Well, you know that if you don't have mass for both, well, you can cancel mass out because it's on both sides. Height, you can't do that because there's no height on this side to cancel out. So for this answer, it would just be no. Mass does not matter because you can factor it out.